integral z to infinity 1 over root 2 pi sigma squared e to the power of minus 1 over 2 sigma squared phi plus nb squared. Okay, the problem with any integral in, this is d phi. The problem with this integral is that any integral in e to the power of phi squared cannot be calculated in closed form. But what we do is we define a special function. The advantage to that is that values of the special function can be tabulated as long as you translate your result back into the special function. You can look up this value in a table for arbitrary NB and sigma squared. That special function is called ErrC, which stands for error function complementary, and it's defined as follows: ErrC of t is equal to 2 over root pi integral from t to infinity of e to the power of minus u squared u. So the trick is to turn this into some form of that. So, think way back to calculus, your first year calculus course. So, what we basically need to do is we need to do a change of variables from phi to u. And it looks like the easiest way to do that is to say let u equal, basically what we want is to substitute this e to the power of, so that it's just u squared. So let's let u squared equal 1 over 2 sigma squared phi plus n0 nb squared. So that means u is equal to 1 over the square root of 2 sigma squared phi plus nb. We need two things. We need to solve for phi. Phi in this case is equal to u root 2 sigma squared minus nb. And we also need, because we need to switch d phi to du, we need to take d phi by du. First derivative of this with respect to u is just root 2 sigma squared, and that means this term is 0. d by du of that is 0 because it's constant with respect to u. So therefore d phi is equal to du root 2 sigma squared. Okay, now let's substitute on this side. Interpretation of these limits of integration is integral from phi equals z to infinity. So substituting in for phi, I have u root 2 sigma squared minus nb equals z to infinity 1 over root 2 pi sigma squared e to the power of, okay, this big mess under the exponent, I deliberately set it so that this is equal to u squared, so I can just substitute that directly. then I stick in d phi with its du equivalent, and I get du root 2 sigma squared. So what I end up with, that 2 cancels with that 2, that sigma squared cancels with that sigma squared. Down here, the limit of integration is u is equal to z plus nb divided by root 2 sigma squared. At the upper limit, normally I would also have to do that, but it's not too hard to see that that's still infinity. And we get 1 over root pi integral from u equals z plus nb over root 2 sigma squared to infinity of e to the power of minus u squared du. So, ERF C was expressed this way. ERF C of t is 2 over root pi integral from t to infinity of e to the minus u squared du. So if I compare these two, what's different? I have a 2 here and a 1 there, and other than that, everything's the same. So therefore, this is equal to 1/2 ERF C of z plus nb divided by root 2 sigma squared. So another advantage of ERF C is, okay, well, 2 advantages. Like I said, it's tabulated in tables, and secondly, there's a MATLAB defined function. So if I gave you z, nb, and sigma squared, you could go to MATLAB and tell me the probability of error. Oh, I'm sorry, I made a mistake here. Oh, no, I'm sorry, that's correct. My notes are slightly different because they're a little more general. So for a second I thought I'd made an error, but this is right. Okay, so that is the probability of error given that a 1 was sent. Probability of error given that a 0 was sent. The only real difference is that this is minus. Well, 2 differences. That's minus, and this is from minus infinity to z. I will leave it as an exercise for you to show that this is equal to 1/2 ERF C of NB minus Z divided by root